So this is section 6.3, the binomial model. In the previous section, 6.2, we looked at how the normal model fits many real-life continuous numerical variables, but we've already talked about that we also have discrete numerical variables. And so what model can we use to describe discrete variables? And that will be our binomial probability model. The results of a random experiment may be modeled by the binomial probability model if the outcomes you're interested in are counts. And the 4 characteristics below must also be present. So we're always going to need to check these 4 characteristics to know whether or not we can use our binomial model. So, number 1, there must be a fixed number of trials. The number of trials are represented by the letter N in the binomial model. Only 2 outcomes are possible at each trial, and they're referred to as either a success or a failure. The probability of success is the same at each trial, and the probability of success is represented by the letter P. And the trials are independent, as in the outcome of one trial does not affect the outcome of another trial. So let's look at some examples. An example of rolling a random experiment that can be modeled by the binomial probability model is rolling a fair 6-sided die 6 times and recording the number of ones. Okay, so let's go through our requirements. There are a fixed number of trials. We said that we're rolling it 6 times, so n is equal to 6. There are only 2 outcomes possible at the trial. Notice that we're concerned about rolling the number of recording the number of ones we rolled. So there are only 2 outcomes. Success is rolling a 1, and a failure is rolling anything else, the 2, 3, 4, 5, or 6. The probability of success is the same each time. So every time we roll a die, we have the same likelihood of getting a 1, which is 1/6. And the trials are independent. The outcome of one roll does not affect the outcome of any other roll. So this is an example of when it would be good to use the binomial model. Okay, a second example of a random experiment that can be modeled by the binomial probability model is flipping a coin 2 times and recording the number of heads. So there's a fixed number of trials. We're flipping a coin 2 times, n equals 2. There are only 2 outcomes in the trial. Success is getting a heads, failure is a tails. The probability of success is the same at each trial, and that is 1/2, and the trials are independent, as in the outcome of one toss does not affect the outcome of another toss. Another example of a random experiment that can be modeled by the binomial probability model is flipping a coin 4 times and recording the number of heads. There is a fixed number of trials, n equals 4. There are only 2 outcomes. Again, success is heads, failure is tails. The probability of success is the same. It's 0.5 or 1/2, the probability of flipping a heads. And the trials are independent. The outcomes of one coin toss does not affect the outcome of any other coin toss. So the following sample space lists the outcomes for this random experiment of flipping a coin 4 times. So for example, one possibility would be getting tails, tails, heads, heads, or tails, heads, tails, heads, and so on. And you can see that there are 16 possible outcomes in our sample space. So what is the probability of flipping 0 heads? That happens when we only flip tails, and that only happens 1 time in our sample space, so that would be 1/16. What's the probability of flipping just 1 head? And so 1 head is here, and that, oh, I missed one, is 4/16. The probability of getting 2 heads is 6 16ths. You can count this up in your sample space. The probability of 3 heads is 4 16ths. And the probability of getting 4 heads is 1/16. What do these probabilities add up to? If you add up the column, they all add up to 16/16 or 1. Use the probabilities to complete the probability distribution below. Okay, so the probability of getting 0 heads we saw up here in our table is 1/16. If we convert that to a decimal, that's 0.0625, 0.25, 0.375, 0.25. This helps in drawing our probability distribution down here. So of getting 0 is pretty small, 0.25. Probability of getting 2 heads is 0.375, 0.25, and again, a 4 is 0.062. So that is a probability distribution based on our binomial model. The binomial distribution depends only on the values of the number of trials, the probability of success. And so the notation for the binomial distribution is B for binomial. The first number listed is the number of trials. The next number is your probability of success. And X is used to represent the number of successes you're interested in. So the probability of getting 2 heads, so that's the number of successes we're interested in, would be listed as, in our experiment, was our N was equal to 4. The probability of getting a success ahead was 0.5, and what we're interested in is 2. So once an experiment has been identified as a binomial and these values have been defined, you can find the probability any way you wish using one of these options. You can use the sample space like we listed before on the other page. You can use a binomial probabilities graph like we just created on the previous page. You can use technology such as StatCrunch. So in StatCrunch, you can go to calculator, binomial, and a binomial distribution will pop up, and then you can input the information specific to your distribution, as I've done here, where N equals 4, P equals 0.5, and we're interested in exactly 2 successes, and we see the probability is 0.375. You can use a table of probabilities like there is in the back of your textbook. We'll look at this in a minute. Or you can use this formula, which we are not going to focus on in this class, but it is a formula that can be used to calculate probability. So let's use these first 4 methods to find the probability of getting 1 head when a fair coin is tossed twice. So actually, let's write out what, using our notation, we have our binomial. The number of trials is 2. The probability of a success is 0.5. And what we're interested in is the probability of getting 1 head. So that is using our binomial notation. Now let's go through and list the outcomes in the sample space. So all the outcomes are getting a heads and a heads, a heads and a tails and a heads and a tails and a tails. Use your results to complete the following probability distribution. The probability of getting 0 heads is 1/4. The probability of getting 1 head is 2/4, and the probability of getting 2 heads is 1/4. So what is the probability of getting 1 head? That is equal to 1/2 or 0.5. Now, using the graph below, we can do the same idea. We can confirm what we found in part A. The probability of getting 1 head is this line here, and it tells us that it's 0.5. And this graph was created in StatCrunch. So using the binomial calculator, as I just showed a minute ago in StatCrunch, you would plug in n equals 2, p equals 0.5, and then you're interested in, this is an equal sign, that x is equal to 1, and the answer comes out right here, 0.5. It also creates the probability distribution graph. So we'll get some practice with this in our group activity. And then finally, using the table from the back of the book. So you just have to follow along to find all of the essential pieces of information. We are looking at n equals 2. We have p equals 0.5, and our x is 1. Okay, so we're going to go into this one here, follow across till we get to our column that matches with the proper p, and our answer is 0.5. So let's look at a couple of features of the binomial. What would happen if we change the number of coin tosses? The probability of success. For different values of n and p, we have different binomial experiments, and the binomial distribution looks slightly different in each case. So let's look at what happens when we change our n, the number of tosses. So the first one, we have n equals 2. The second one, we have n equals 4. So we have more outcomes possible in the second distribution, but basic shape is about the same. They are both symmetric and centered here. And it looks like they're actually centered, as we'll see later, that if we were to, this one's centered at 1, right? And if we were to multiply n times p, that's 2 times 1/2, that equals 1. And the same thing is true over here. This one's centered at 2. So if we multiplied n times p over here, 4 times 1/2 equals 2. So we're going to see that the binomial distribution is centered at n times p. Now let's look what happens when the probability of success changes. So for all 3 of these distributions, we're looking at n equals 10. So the number of trials is the same. But notice that the probability of success has changed. 0.5, the probability of success here is 0.1, and the probability of success there is 0.9. So the first distribution is symmetric. And unimodal. The second distribution is skewed to the right. And it looks like there's, we'd expect far more failures. So the probability of success is only 10%. And so really the distribution is pretty stacked up over here with expecting to get more failures. Whereas the third one, we're skewed to the left and we're expecting to get many more successes. The probability of success is 0.9. So a binomial distribution can be described by its center, which is its mean, and its spread, the standard deviation. The mean tells us where the distribution balances, and the standard deviation tells us how far typical values are from the mean. What do you think the mean is for each of the following distributions? So the typical value looks like the mean is going to be 1 for this distribution. And as we saw before, that n times p gives us 2 times 0.5, which is equal to 1. And here the mean, the center, is at 2. And again, n times p is 4 times 0.5, which is equal to 2. So the following binomial distribution is skewed to the right. What do we think the mean is of this one? The mean looks like it's probably around here, which is 5. So as I said, it turns out that the mean of the binomial distribution can be found with this formula. The mean is equal to n times p. And let's try that out up here on the one above. So n times p. 15, and our p is 0.3, which is equal to 5. So that would be how we always can find the mean of a binomial distribution. This formula gives us the mean number of successes in a binomial experiment. And this value is sometimes called our expected value. Okay, that's the number of successes you expect if the random experiment were repeated n times. What do we think the standard deviation of this one would be here? So it looks like if we were using what we kind of know about standard deviations, it looks like we're expecting to see maybe, I don't know, like 1.5 our standard deviation, or maybe 1.7. It looks like the standard deviation for this binomial distribution would be about 1.7. Let's go on and find out about how we can calculate standard deviation for the binomial distribution. The standard deviation can be found using this formula. So sigma is equal to the square root of n, the number of trials, times p, the probability of success, times 1 minus p. So let's go through and figure out the standard deviation for each of these distributions. So it's n equals 2 times p, 0.5, times 1 minus p. And this comes out to be 0.7071. How about the next one? Same formula. Sigma is equal to the square root of n times p times 1 minus p, which would be 0.5, which is equal to 1. And finally, the last one, let's check out the standard deviation of the last one, which is going to be sigma is equal to n times p times 1 minus p, which is equal to 1.77. And that's a pretty good comparison to what I would have estimated over here using just what we know about our information being about within 3 standard deviations. Okay, so the most common application of a binomial model is in survey sampling. Imagine a large population of people, such as 100 million registered voters in the United States. Let's assume 50% of them will vote for the Democratic candidate in the next presidential election. Suppose ABC News takes a random sample of 100 registered voters and asks them which candidate they are going to vote for in the next presidential election. So we can use a binomial model. I mean, we think we can use a binomial model, but we need to check to make sure the 4 characteristics of a binomial model are being satisfied. Are there a fixed number of trials? So Above, it says that random sample of 100 registered voters. So yes, they're going to ask 100 people. That's n equals 100. Are there two outcomes? Yes. They're asking if they're going to vote for a Democrat or not. So we could have a Democrat or not, and that will be, our success will be a Democrat. The probability of success is the same in each trial. We think that 50% of them will vote Democratic, which means the probability of success is equal to 0.5. And finally, the trials are independent. And yes, we can assume that each person's making their own decision in the sample. Use the following for the mean and standard deviation of binomial model. Use the formula, sorry. And so we can calculate that. How many registered voters in this sample should we expect to vote Democratic? So this is asking us about expected value. How many do we expect? And we get that is going to be our n times p. So in our case, that's 100 times 0.5. So we're expecting to see 50 voters vote Democratic. Give or take how many? This is talking standard deviation. So let's use our standard deviation formula, n times p times 1 minus p. So that would be 100 times 0.5, which is equal to 5. So in other words, we're expecting to see 50 voters vote Democrat and plus or minus 5 voters. Would we be surprised if 60 registered voters voted, indicated that they'd vote for a Democratic candidate? So 60 voters, no, I don't think we'd be surprised, because that's within one standard deviation of, within 2 standard deviations of the mean. So that's not too shocking. 70 voters. Yes, that would be a surprise, because now we're looking at being 4 standard deviations away from the mean. And that's pretty unlikely to see. And one last comment. Typically, surveys refer to percentage of voters rather than the number of voters when they report the results in the news. The binomial distribution still applies, since we are just converting the counts to percentages. So if we have 50 plus or minus 5 voters, and we think of this as percentages, we're really just saying 50% plus or minus 5% of the voters will vote Democratic in the next election.